machines. My slides are in English, some of them are in German, and some of them are in Greek, so I hope you're cool with that. Abstract machines aren't the kind of machines that you would generally think of. They're not the kind of mechanical machines you would physically build, although they are very mechanical in a way, and you could definitely build them if you wanted to. But abstract machines are machines of the mind. They are the software that we create in our heads, and they're like castles in the cloud. So my name's Igor. I'm from the internet. I've done a bunch of PHP stuff, and I'm currently working at ResearchGate out in Berlin, which is a social network for researchers and scientists, and we're trying to accelerate the scientific process and take a bit of the power away from these old academic journals, which move very slowly. And it's very difficult to get things published in these journals, and it usually takes, so the feedback cycle is like half a year just to get things refined, and we're trying to accelerate that and give a central place for researchers to communicate and to make science better. I'm honored to be here speaking to all of you today. I must confess I am not a Laravel developer, so I've been more active in the Symfony community, which I think we do somewhat share, at least I hope so, since it is sort of the plumbing of the new PHP era at the moment. But I do think we have something in common, and that is that I also have a pet. So we have computers, and they're a bit like Tamagotchis. They're almost like living things, because there's all these processes going on. They're very complex. They're interacting with complex ways. Just keeping a computer alive is very difficult, and you need to push all these buttons and just to make things happen. And this is not only true for using computers. I think this is even more true for programming them. Programming is hard. And I think all of us somehow intrinsically feel this, but we don't necessarily know why. We can't, or at least I personally couldn't explain this for a very long time. And so, come on, technology. Not working.
You forgot to feed it.
Good one. So, why? Why is programming so difficult? And that is really the question that I will try and at least shed some light upon today. But before we can get there, we need to sort of cover a bit more of the basics. So I think there is this very strong link between our world and this computational world that happens inside of our computers and inside of our minds. So in the computational field, you have this thing called cellular automata, which is almost impossible to pronounce, and I shall be attempting to pronounce it during the next few minutes, over and over again. And these cellular automata are self-replicating abstract machines. They model, in a sense, biological processes. And then in our world, in the physical biological world, we have humans that are sort of like biological machines, and you can see this on a bunch of different levels. So you could see this on the per human level, you could see this on a cellular level, or you could even see it on a DNA level, where things are replicating, and they're replicating in accordance to almost mechanical rules. And you could even take a step back and consider the entire universe to be one big machine that is just operating under the laws of physics. Okay. So what is an abstract machine? An abstract machine is a model of computation. It's a way of thinking about what a computer does and about what happens when we run our programs. So you could think about it as a really simple interpreter. So you take a programming language, you remove pretty much everything apart from the core bare essentials, and what you end up with are these really simple models that somehow tell us something about what is actually happening. And one form of abstract machine are these cellular automata. And the most well-known of those is Conway's Game of Life. Has anyone heard of this one before? OK, that's about half the room, I guess. So, awesome, by the way. Conway's Game of Life, I'm just going to go over it real quick, is this system that is based on a two-dimensional grid. And so you have this grid with cells that can be in one of two states. They can be either dead or alive. And then you have discrete time steps in which the entire world, the entire grid, is manipulated in order to, in accordance with a certain set of rules. And the rules are very simple. So for each cell, you look at its neighbors, the surrounding cells, just the 8 surrounding cells. And then if the cell in the middle is alive, it needs 2 or 3 cells, alive surrounding cells, to survive. If it's currently dead and it has exactly 3 surrounding alive cells, it becomes alive. And in all other cases, it is dead or it becomes dead, it dies. And so I can just quickly show you how this looks. So you have this shape that many of you have probably already seen before. It's a glider. And so here we just count the different alive neighbors. And then you see 2 of them have only 1 alive neighbor, so they go away. But then there's 2 other ones that have exactly 3 neighbors, so they come to life. And now 1 time step has completed, and you just repeat this process, and that is how the game evolves. So it's funny how it's called a game, because you don't really have any control about it, and which is kind of true about life itself as well, at least to some extent. There are external factors. OK. And so if you keep going with this and you reapply these rules, then you can actually see that there is some sort of movement. There is some sort of shape that is moving across this grid, which is really amazing, because I didn't encode anything about shapes. I didn't encode anything about moving objects. So you have rules that are only specific on the local level. The rules only concern themselves with the individual pieces, but if you look at it from afar, you can recognize patterns, and you get this emergence of very complex behavior that you can only recognize on a high level, and on a low level, it just looks like things triggering, right? And you could think of the brain and neurons sort of just doing stuff on a low level, and then consciousness happening on a higher level. Just as a side note there. So you can build very interesting stuff with this type of system. And one example of that is this, which is known as the Gosper glider gun. So if I just run this, and I hope it's running, there we go. So as you can see, there is some sort of stationary aspect there, but then it's shooting out these little gliders. So it is a gun that is producing new gliders all the time, which is amazing. So there's a bunch of different types of shapes that you can make in the game of life. They're usually categorized this way. So you have still lives that just are stationary and don't move at all. You have oscillators that toggle between a bunch of different states. You have spaceships that move around. And then you have guns producing spaceships, puffers leaving behind a trail of destruction, and breeders, which are like moving guns. So there's spaceships that produce guns that then produce new spaceships. So a lot of complexity from very simple rules that I could explain in 1 minute. OK, so this is a cellular automaton. It's kind of a metaphor for life. And I do want to show you one thing. So if I run this, I'm just going to randomly generate a grid. Oh, let's try again. How's that? Better? Yeah. So I'm just going to randomly generate a grid, and you're just going to see things moving. And this is completely randomly generated, and it starts out as a big boiling mess of stuff just moving around all over the place. But then after only a couple iterations, you can, for one, you can start seeing patterns, but everything sort of starts to slow down, and most of the things just die, and then there's a couple things that are just sort of stationary, and especially those blocks are extremely common. And so if you leave this running for just a minute or so, it's going to be mostly just wasteland. Another metaphor for life. Actually, let me cancel that. There we go. So you get this complexity, which is very interesting. There's other types of cellular automata. I do want to show you two more of them because I just think they're really, really awesome. So the first one is a thing called wire world, and this operates under the same type of rules. So it's also only looking at its neighbors. It's got a slightly different configuration with 4 states instead of 2 states, but the general idea and the general mechanism is identical to the way that the game of life works. And this one, if I just run this, looks quite a bit different. So you have, it acts a bit like electronics, right? And this thing actually is a type of computer. I believe it's an adder that is adding 2 numbers in binary. And you can model this using the same system that somehow models life. So there's already an interesting kind of analogy going on there. And then there's this other thing called the Langton loop. And so what this is, I'm just going to run it. So it's a loop that contains information, and the information flows around, and then it sort of splits out. But as you can see, there's sort of 2 interpretations of what that information means. For one, it's just sort of contained in this loop, but it's also a set of instructions for replicating the loop itself. So this is almost like how DNA replicates itself by interpreting the data in 2 different ways. And this also leaves behind a trail of destruction. Once again. This is amazing. OK. I didn't do anything. I just pressed the button. It's OK. So let's get a bit more serious. Let's try and imagine the simplest possible machine that one could think of or possibly build. And that might be what is known as a deterministic finite automaton, or also known as state machine, or also known as regular expressions. So this is what it looks like. And you can represent it using a state transition graph, which really just means a bunch of circles and arrows between them, like this. And this is the equivalent of this regular expression. And if I zoom in here a bit, you can actually see, the different cases, right? So you have refs, fixes, closes, and you have closes at the top, fixes in the middle, and refs at the bottom. And there's always 1 character per arrow. And then you can look at the second part, and there's this little loop thing going on. So the circles are states. The arrows are transitions between those states. And the way that you would run such a machine is by taking some sort of input, which is usually an input stream or an input string, and you consume the stream character by character. And then all you do is you have this pointer, this red arrow, that points at a certain state, and then you look at the outgoing states, you look at the consumed input character, and you just follow the one that was there. So in this case, we follow the F, because that was the F, and if you don't find one, then you just fail instantly. But as long as you find things, you just keep going. And the only piece of information that this machine has is the arrow. It's just a pointer to a state. And so you just keep consuming, and with every character that you consume, you just move along in this state machine. And then you have these numbers, and so you stay on the same state. So the regular expression star really just translates into a state that references itself. And then at the end of the input, you check if you were in an accept state. So double circle means accept state. And so if you're done and you are in an accept state, then all is good. And you accept the string, and otherwise you reject it. And this is equivalent to regular expressions. So regexes are actually compiled into something like this. Blah, blah, blah. So where is this used? This is used, well, for regular expressions, obviously. It's used quite a lot for lexical analysis, which is tokenization, which is a part of parsing, which is used in a lot of protocols and programming languages and such. It's used for network protocols, but I think it's just, even as a general way of thinking about state transitions, it's very useful where you have a finite amount of states, which you have quite often in things like games and just business rules where you want to validate that you can't go from like the final state to the beginning state or something like that. So just thinking about programs in terms of this and somewhat modeling it like that can help a lot. This is an implementation of this type of thing. So it's really just 2 lines of code. It's a for each loop that goes over the input and then looks up something, and then assigns the new state. And that is it. Very simple, right? OK, any questions on this so far? I'll keep going then. Very well. So what if we wanted to make something that is more complex, that is more powerful? Well, so the DFA, the deterministic finite automaton, is deterministic. Maybe we could replace that with non-determinism and make it more powerful that way. So what does determinism mean in this case? It really just means that from any given state, you have a unique way of knowing which next state you will end up in. So it really just means you can't have multiple arrows with the same thing on it, and each arrow must have something written on it. So with this non-deterministic variant, you can have empty arrows that you will always follow. So let's try and introduce that. So these strange Greek E, epsilon characters over there really just mean empty, and an empty transition is one you always follow. So if we try and execute this, and this is a regex that matches foo, bar, or baz, very creative, I know. And so you follow that, and at some point you realize, well, I'm consuming a B, so the first branch just goes away because that wasn't a B, so you can't follow that. But you need to keep multiple pointers in this case, so there seems to be more complexity there, at least in the implementation of such a thing. And so you go along, and then the other branch goes away, then you need to consider both of these again, and then you go to the end, and all is good. Now, it turns out that this machine is not actually more powerful than the deterministic one. As a matter of fact, it is equivalent because you can take any non-deterministic one and compile it down to a deterministic version of it, which is not that obvious at first, right? At least it surprised me quite a bit. But the previous example already kind of showed this. And you can think of this as parallel timelines on a fixed time scale where there's a certain overlap. So here you can see the overlap, and you just collapse those into single states, and then you end up with something like this, which no longer has these epsilon transitions, therefore is deterministic. OK. So let's try and actually add some power to such a machine. So what you do is you go down to the shop and you buy a stack. And you just take the stack and plug it into the DFA, and then you have a pushdown automaton. So this is a stack version. This is what it looks like, by the way. This is the official thing. And yeah, it's pretty much a DFA with a stack. So what can you do with that? Well, you can accept nested structures, which is something you simply cannot do with regular expressions. So this can actually accept most languages. So the simple example is balanced parentheses, but you can do something like JSON parsing or parsing the PHP language with this, which is actually kind of surprising considering the previous thing was just this two-line loop, and this doesn't seem that much more advanced than the previous thing, but it already can do way more advanced stuff. So how would you do that? The example I'm going to show is the balanced parent, simply because it's a bit smaller than like the whole PHP language. And so this is the formal grammar that defines how a language of balanced parents looks like. And you can take one of these formal grammars. You find these in most programming language implementations. So you have parser generators that you feed it one of these, it compiles it down to this pushdown thing, and then it just runs through it and parses it all out. So what you would end up with is something that looks something like this. And so this is still fairly similar to the previous type of thing. However, the rules have more things, like the arrows have more things written on them. So not only are you matching on the input character that is coming from the outside, you're also matching on the current top of the stack. And once you've completed a rule, you push something new back onto the stack. So stack being a data structure where you can only access the top, and you can only pop things from the top and push things back onto the top, which kind of looks like that. So that's the official stack logo. And because computer scientists don't know how to say that something is empty, you always need to put a symbol in that symbolizes emptiness. It kind of defeats the point. But anyway, this E means that it's empty. And you can think of this stack as going off to infinity at the top, which is a nice thing to have. And so you still have this red arrow pointer that points to a certain state. And so you consume the input. And in this case, the first rule matches. And as we go along here, what you can see is that for every opening paren, it will push an X onto the stack. And for every closing paren, it will remove an X from the stack. Fairly straightforward. And then only in the end, only if you match on the actual E on the empty stack can you go to the final state, and otherwise it rejects. So this is a more simple example, but using exactly the same principles, you can build a parser for pretty much any language. Blah, blah, blah. So this is useful for validation parsers, and also as a general model of thinking about stack-type operations. So, for example, the way a calculator works, it also uses a stack. The way an interpreter works, it also uses a stack. It uses a call stack, and every time you call a function, it pushes the current context onto the stack, then continues inside that function, and then at the end of the function pops that previous context and sort of goes back into there. So just knowing about this kind of stuff and understanding the general model can help you think about the execution flow of programs. And this is what it looks like. So if you were to implement such a stack machine, it's mostly the same code as previously, just with this new stack thing added at the top, pushing some stuff at the bottom, and matching the rule based not only on the state, but not only on state and token, but also on the top of the stack. Fairly straightforward. Any questions about this so far? Over your head, or all good? This is nothing. Yes?
So kind of the point of what you're doing here is just, it's almost like validating the structure.
Yes. So the These automata generally are used for validation only, but with some very simple extensions, you can get parsing as well. So you just have you plug into certain states and say, whenever this state is activated, I want to write something out. Yes?
I think I got a question.
Go ahead.
Here we go. So, I'm thinking regular expressions. I'm looking for an answer on this one. Why wouldn't I use regular expressions with what you're doing in comparison? I don't understand.
So, is the question what's the difference between a stack version and a regular expression?
You can pull out of what I'm trying to say there.
So with a regular expression, you can parse nested structures, but only to a finite depth. So you would have to hard code the amount of depth that you want to parse. Think of JSON, for example, where you can have an object containing an array, containing an object, containing an array, and so on and so forth. So with a regular expression, you could sort of hard code the possibilities to some arbitrary depth. But due to the structure of the thing, because it's finite, I could always make a larger nested JSON structure that wouldn't validate. And with this, you can. I hope that somewhat answers the question that was somewhere floating around there. I'm trying really hard here. All right. Let's carry on then. So now we are going to talk about the one machine to rule them all, the Turing machine. And this is what it looks like. So Alan Turing lived a pretty remarkable life. He created the idea of computers, or rather the field of computer science, before it even existed. Then the war kind of happened, and he destroyed Nazis with his mind. Then he created the field of artificial intelligence. Then he went on to work on some of the first actual electronic computers and died a spectacular death, something to do with chemicals. So Alan Turing was working on this problem called the Entscheidungsproblem back in 1936. And so he wrote this paper, which is sort of the defining moment of starting computer science as a field. Well, technically, there was this other guy called Alonzo Church. We don't really talk about him. He's like a strange functional programming guy. But he was a couple months earlier, but let's stick with Turing. It'll be fine. So I want to just show you the machine first, and we can talk about the background of it after that. So this is a Turing machine. It's a DFA, but it's got, instead of a stack, it's got an infinite tape attached to it. And this tape acts as both the input and the output. So you no longer have an input stream, but you just have this long tape that kind of goes off to infinity on both ends. And the rules of the machine, so the arrows between the states, they tell you, or they tell rather the machine, if it should go to the left or to the right, and based on which value it read, which one it should write. So that's all it does. Read, write, left, right. Yeah? So here we have a tape, and here we have a pointer pointing to a state. And so given this initial value of the tape, this particular implementation of a Turing machine is actually a binary adding machine. So it is rather a binary increment machine, sorry. So you give it a binary number, and it just increments it by 1. Pretty basic, but it would be kind of surprising if such a simple machine that only follows arrows could do something like that. So let's see how this works. So this is a binary 3. We're going to try and increment it to a binary 4. So let's try. So it matches the first state because it it reads a 1, and the rule says read a 1, write a 0, go to the left. So it writes a 0, goes to the left. Then the same rule matches again because we're still in the same state and we're still reading a 1. So read a 1, write a 0, go to the left. So now we read a 0. So it goes to this other state which says write a 1 and then go to the right. And then we have this thing at the top which says read 0, write 0, go to the right. And the same thing for 1. So it essentially just means seek to the right until you hit a blank, which is a sort of a strange way of encoding that. But using these rules, that's kind of how you do it. So it just goes to the right, finds the blank, and then goes to the left, and that's it. And if we look at the result, it's a 4. Yay! So let's just try it again, just to be sure that it actually works. So read a 0, write a 1, go to the right, hit a blank, done. It works. Nice. So this is a machine that consists of a set of states. That's what the Q means. It has this infinite tape, which is like the strange T-looking thing. The epsilon is, what was that one? The input alphabet, so the amount of the set of characters that you can use in this machine. The squiggly, circly thing, which looks like one of these logos. Delta, yeah, that's the one. That's the transition rule. Q0 is the initial state. B is just a B, you know. And F is the set of accept states. So that's Greek for you. So what's interesting about this machine is that it can run any algorithm. This machine can run any algorithm. So just try and think about what that means.
Is this Laravel 5?
Could be. So what this means is that any idea that you can think of, anything that you can come up with, any electronic device that you own, your iPhone, your computer, whatever, can be simulated by one of these machines. It's probably going to be slow as hell, but it's possible. And that is pretty significant because like, this thing doesn't do anything, but it does everything. This is what it looks like. And it's just 20 lines of code. So you don't need PHP anymore. You don't need Laravel anymore. Just use this. So this is my framework. It's called Turing PHP. So one of the big differences to the previous code samples is that this one has this while loop. And the previous ones were using a for each loop. And this is a huge difference because this loop is unbounded. And that means that there is a potential for this loop to just go on to infinity. All of the previous machines were bounded by the length of the input. Well, in this case, the input itself can be infinite, since the input is the tape and the tape is infinite. And so we have this new problem, or maybe it's not a problem, maybe it's a power, we're going to find out, of infinity. So this is kind of a new concept, and this is the distinguishing difference between this kind of machine and all of the previous ones. So this is an encoding of the rules of the increment machine that I showed you previously. And what I want you to realize here is that it's just a set of data. It's just a table of some numbers, and that is going to be important shortly. So there's a couple interesting implementations of Turing machines. There's this one, which was done with Legos. Another one, which is sort of a hydraulic type of system that technically doesn't even need any electricity at all. So you just push the pump, and it calculates stuff. There's this one, which is a bit closer to Turing's original idea with the paper tape, which is quite nice. OK, so there is this property of universality that I want to talk about. And so this guy, Konrad Zuse, who was working on one of the first actual electronic computers, he said this: for every problem, there is a special purpose brain that solves it as fast as possible. Now, he wasn't talking about an actual brain. What he was talking about was an algorithm. So there's a specific algorithm that is optimized for a certain type of problem. And if you take these Turing machines, you could implement an algorithm using a Turing machine. But every time you do that, you're kind of building a specific machine for that thing. And even if you have a somewhat generic machine with wires to plug in, it's still kind of annoying to have to rewire that by hand, right? Which, the early computers, that was what programming was. It was rewiring things. So if we have these special purpose machines, these special purpose brains, well, what are they? They're really just a bunch of data. They're just a bunch of numbers. They're a description of these state transitions. And since they are just a bunch of data, what can we do with data? Well, we can write it down. And once it's written down, what can we do with it then? Where could we possibly write it? Well, how about we write it to the tape of another Turing machine? And then, how about we create a universal machine that is able to read that description from the tape and simulate it? So this way, you can take any algorithm and not have to build a new physical machine, but just write it down, run it through the universal machine, and be happy. And at this point, you can also build a universal machine, write that universal machine to a tape, and have the universal machine run itself, and so on and so forth, which is also kind of fun. So now this thing can run any program, and you no longer have to rebuild or rewire it, which is kind of nice. And this is, so here's one implementation of that. This is an actual universal Turing machine, pretty impressive. Only using 16 or so states, which is also quite amazing. So this is essentially the same idea as John von Neumann's stored program computer, the von Neumann architecture, which is really just translates to software. Okay. And this idea of implementing a Turing machine in terms of a Turing machine is kind of similar to implementing a programming language in terms of a programming language. So what if you wrote PHP in PHP? Well, someone actually did that, so there's that, which is also incredibly cool. Now, there's this property of Turing completeness, which means any system that is capable of emulating a Turing machine has this property. And you actually don't need that much, you don't need that many things to build a Turing complete system. So what you generally need is some form of unbounded storage. You need a way of conditional branching, so doing either this or that. And you need some form of recursion or looping. And that's pretty much it. So there are actually a number of systems that you wouldn't expect to be Turing complete, but they still are. And we're going to see some of those a bit later. And we're actually going to see some of those right now. So one of them is a universal Turing machine already, yes. Again, there's the lambda calculus, which I mentioned briefly earlier. Now it turns out that the game of life is also Turing complete. So you can actually build a computer using the game of life, which is pretty crazy, right? And then there's things like brainfuck, which is an esoteric programming language that makes the life of the programmer as hard as possible. But you can still do pretty much anything with it. You just need to do it with enormous difficulty. So PHP is also Turing complete. And there is this implication that a system that is Turing complete, that is, a system that can implement a Turing machine, that this also goes the other way around, meaning that a Turing machine can implement that system. So a Turing machine, you could write a Turing machine that runs PHP programs. Just think about that. And if that is true, if PHP is Turing complete and can only do as much as a Turing machine, then why should we even bother with PHP? Why shouldn't we just all be using Turing PHP or a Turing machine directly? And this is an easy trap to fall into, where you say, well, you know, all programming languages are kind of the same because they're all Turing complete, you know. But the problem here is that from a programmer's perspective, that is not true at all. So even though at a computational level they are equivalent, it's just a lot less convenient to use a Turing machine. It is a fucking pain to program one of these things. So there's this beautiful quote by Alan Perlis, beware of the Turing tar pit, where everything is, what was it? Everything is possible, but nothing of interest is easy. And this is, I mean, we're not programming in assembly language anymore. So there we go, right? Also, this paper, Epigrams on Programming, is the most quotable computer science paper ever. It's just like one punchline after the next, and you can just tweet all of them and get a gazillion retweets and be famous. So read it. Now, one of the things that you can do with Turing-complete systems is that they have this form of self-reference. And there's two types of self-reference that I want to talk about. One of them is the ability to produce quines. And in this case, this is a special form of quine. So a quine is a program that produces its own source code. Let me show you. So actually, let me first echo out the code. That's the quine. And if I run the quine, it produces the quine. And then if I pipe that quine into PHP, it produces the quine. And so I can just keep doing this. And it gets slower every single time, but it still works. Now, what's interesting about this quine, though, is that it has access to its own source code. So it has the full copy of its own source code as a variable in the program. So you can do some pretty interesting stuff with that. And so one thing that I experimented with was taking the general structure, but then not just echoing out this program source code, but actually modifying it just a little bit. So if I run this program, then you can see the number n, which is 1. So if I pipe this into PHP, then you can see it increments. If I pipe this into PHP, then you can see that it's 3. And if I pipe this into PHP, then you can see that it's 4. I should have made this a lot shorter. If I pipe this, and I can't type, into PHP, then it's 5. And if I pipe it into PHP one last time, then it produces a new result. So this is an algorithm that sort of rewrites itself to produce something else in the end, which is pretty amazing. So that's one form of self-reference. A different form of self-reference is recursion. And can anyone guess what this program does? So someone, when I did this presentation at a local user group once, someone said it would use a lot of memory, which is true. It's the same as this. So it's the functional equivalent of an infinite loop, which might not be that expected. It's also the same thing as this in terms of Turing machines. It's the same thing as this in terms of lambda calculus expressions, which is kind of where I took the first example from. And so this type of recursion caused a lot of issues in the early 20th century mathematician community, where they were discovering all of these paradoxes in relation to self-reference. One really well-known one is Russell's paradox, which formally is, does the set of all sets that don't contain themselves contain itself, which is often rephrased as this barber paradox, where there's a town where there's only one barber, and everyone does one of two things, like not both, which is either shave themselves or go to the barber. Then the barber shaves all who don't shave themselves, but who shaves the barber? which is really just an advanced version of this liar paradox, which says this sentence is false. Well, if it's false, then it must be true, but if it's true, then... So this is caused by the self-reference, by the sentence, or the statement in this sentence, being able to refer back to the sentence itself. And so, since this was an issue in set theory, which is sort of mathematically important, they really tried hard to figure this out. And they came up with a bunch of different approaches, such as type theory, and creating a hierarchy and saying this can't contain that, and sort of only larger things can contain the other things, and trying to keep this self-reference out. And they started formalizing a lot of mathematics by creating these axiomatic systems that are a lot like the automata that I showed you, just sort of shifting strings around and replacing things on a very low and sort of typographical level. And then in 1931, this guy Gödel came along, and he was like, nope, I'm just going to destroy all of you. And so he came out with this thing called Gödel's incompleteness theorem, which kind of proved that no matter how advanced or how restrictive such a system is, once it has reached a certain level of power where it is able to do certain things, there is some form of self-reference. And because of this, there is a way of making statements that are true but not provable. So in essence, he showed that you can't prove everything using mathematics. There's always things that are true but not provable. And then Turing came along, and he was working on a similar problem called the Entscheidungsproblem, which formally is blah, 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 first-order logic stuff. But there's an equivalent thing to this to this Entscheidungsproblem, decision problem, which is the halting problem. And the halting problem is that of deciding whether Turing machine is going to halt or not. Or in other words, take a look at the source code of a program and decide if there is an infinite loop in there or not. So that is kind of interesting to us as programmers, because has anyone ever run into an infinite loop in a program before? There you go. And this can happen very subtly. I mean, if you have, for example, if you have events, and then you have two event dispatchers, and this one is throwing that event, and this one is throwing the other event, and they're sort of calling each other, you might not expect this to go off in an infinite loop, because they're sort of dislocated in different places. So these kind of interactions can happen in very unexpected ways. And that's why it's very relevant to us as programmers, because it's so easy to create these type of bugs in our programs. So I'm going to present to you the proof that Turing made. So what he did was he assumed that this machine exists. It's called a halting machine. It takes a program, or rather a description of a program, and the input to run on that program, and decides if the program will halt on that input. Halting meaning stopping, meaning lack of infinite loops. So to this halting machine, and this thing will only statically analyze the program. It won't run it. That's the critical thing. It doesn't run it. It decides. So you attach to this negator, which just does the opposite. So if the halting machine says, yes, it will halt, then the negator will say, yeah, I'm just going to go in an infinite loop. And in the inverse case, if the halting machine says, this is going to be an infinite loop, then the negator just stops. OK. And then you attach to the top a copy machine, which just takes a description of a machine and splits it up and feeds both of it into the halting machine. So the combination of those two essentially check if a certain description halts when it's fed itself as an input. So since we assume that this halting machine is a Turing machine, that means it's just a set of rules. And since it's just a set of rules, what we can do is we can call this thing x, and then we can write it down, and then we can call x of x. So what happens when we do this? So the x goes in, gets copied. The halting machine checks if x will halt on x. So there's two possibilities. Either the halting machine says, yes, it will stop. There's no bug in this program. In which case the negator says, nope, I'm just going to go on forever. Now the problem is this entire thing, this process is the equivalent of calling x on x. It is x on x. So the halting machine said that this thing would stop, but the negator didn't stop, so the halting machine was wrong. Now, if we try the other case where it says false, then we have the same problem because it says false and the negator stops. So again, it doesn't match the thing that actually happened. And using this proof, the only possible conclusion that can come from this is that this halting machine cannot exist. It's a proof by contradiction, and it just shows that there's no possible way they can write a program that analyzes another program and, for the general case, decides if it's going to stop or not. And this is a pretty big result. This is kind of bad. So this kind of shows that we're screwed because we can't do proper static analysis. We can do some static analysis, but there's always going to be certain types of bugs that we simply cannot find. Or rather, we need to find them ourselves, and we can't have an automated way of finding them, apart from maybe trying all the possibilities. But even then, if you have a program that is going on for a very long time, you don't know if it's going to maybe stop in 2 years because it found like, the final digit of pi or whatever. So yeah, this is kind of a problem, right? So how do we cope with that? How do we cope with this issue of Turing completeness? And I have a couple ideas. So you can just be angry all the time. And I'm sure many can sympathize with that, at least at times. You can drink. But there are some better approaches. So one of the things you can do is to use finite state machines, because finite state machines don't have the same power as Turing machines. So if you build a system that is dealing with a finite amount of states, then you can encode it in such a way that there's no way it can go off into an infinite loop. You can use bounded loops. So in PHP, that just means use for each. And I guess that's kind of what we do in PHP, so we're kind of good on that front. So this already helps a lot, because those types of loops will always be bounded by the size of the input, assuming that you're not using some sort of infinite generator or iterator, which can happen as well. Yeah. And you can use type systems. And I think especially with Hack coming out now, there is a lot of potential there for having more correctness and more compiler-enforced correctness, because type systems give you certain guarantees. They are restricted forms of computing, and they prevent certain bugs from happening categorically. Now, it's worth noting here that type systems aren't the solution to everything. There are some pretty advanced type systems that can prevent a lot of bad things from happening. But still, in most strictly typed languages, you still have bugs. Just worth noting. OK, so what is the conclusion here? The first conclusion that I'd like to draw is that programming is hard. And I hope I have been able to somewhat convince you of that. So if we step back a little bit and look at the big picture here, we have this hierarchy of different classes of computation. This is what is known as the Chomsky hierarchy, which is based on the linguistic side of this. So you have this duel between these different types of languages and different types of automata that are able to accept those languages. There's a direct correspondence there. And with increasing power, you kind of travel up this hierarchy, where each thing sort of includes the stuff below it. And then we have at the very top of this hierarchy the Turing machine. Now, why is this the complete top of everything? I mean, is there anything above there that we just haven't found yet? That is kind of an interesting question to me. And so I promised that I would show you a few more accidental Turing machines. The most interesting one is Magic the Gathering. So you can actually form any computation using Magic the Gathering, which is nice. But it's probably even slower than most Turing machines. Minecraft, I'm sure many of you have seen computers built in Minecraft, which is pretty cool as well. Microsoft Excel, someone actually built a Turing machine in Excel. So there's this thesis by Turing and Church, Alonzo Church, that is, which is that any Turing complete system kind of goes in both ways, and that Turing completeness is sort of almost the end to everything and defines the top level of what computation is, and that there's some sort of equivalence between that and the brain. Now, you could think of the brain as just a machine. But is there anything beyond Turing machines? And there's been a bit of research into this area. So there's a couple really crazy ideas, like taking a Turing machine, going into space, going to a black hole, and like, as space-time bends, it kind of goes off to infinity. There's a Xeno machine, which takes 1 second for the first computational step, takes half a second for the next one, takes a quarter of a second for the next one, and just always halves the time. And at the end, you've done an infinite amount of steps in a finite amount of time. It's kind of ridiculous. But I think the most promising one is actually quantum computing, which has an actual scientific backing that seems quite promising in terms of being not simulable by a Turing machine. So that is quite interesting, and we might, maybe not in this lifetime, but maybe in 200 years, they're going to be able to do some interesting stuff with that. So is our universe Turing complete? I really don't know, but maybe. So there's kind of a few different possibilities here, right? Either it's less than Turing complete, meaning everything is kind of pre-recorded and just playing back. Maybe it is Turing complete, or maybe it is more than Turing complete. And one example that kind of exemplifies this is truly random numbers. Can you give me an algorithm that generates a random number? It's kind of impossible, right? Because the definition of having an algorithm for that kind of means that you always get the same result. And so you can have pseudo-random number generators, but you always need to seed them with some sort of initial value. And so you just push the step one thing away, but you still need to get a random seed. And since there's no algorithm to get that, we need to do weird hacks like taking information from the environment and looking, like measuring the air around us or whatever, and hoping that that's going to be random enough to not be predictable. But in theory, given the laws of physics, it is kind of predictable. And if you look at the way that physics works, what physicists are trying to do is really find an algorithm for nature, right? And so you could see the Big Bang as sort of this initial value. And if you seeded the Big Bang with the same initial value, you would kind of get exactly the same result. And if we ever find a way to reverse engineer that and find that value and find all of the laws of physics, then we could run a little micro-universe inside of our universe, which would be kind of neat. And then we could try all different mutations and see what happens. I'm looking forward to that. So I want you to take this away from this talk, that the universe is some kind of machine. It might not be a Turing machine, but it is some form of machine. And that's it.
I can't possibly let you ask questions right now. So you'll have to save that for after. One question. All right.
Put your Turing PHP on GitHub?
It is.
Oh, really?
He's already ahead of you.
So
Because he's a genius. Do you see that?
can you put the screen on real quick?
Did you make a Turing machine that's what your Turing machine was?
So I have one right here. So read these books and go to Joined In and rate this talk. And there's all of the GitHubs.
Thanks. It's great.